Hello, I'm Nigel Griffiths. I work in the Advanced Technology Centre in the UK, which is part of IBM Europe. In this active memory sharing, we're going to look at the concepts behind AMS before we actually give it a go. In this movie, I'm going to assume that you know the 5 paging golden rules, what a working set is or a resident set, and who owns the page tables. If we're not aware of that, then I recommend you first look at the movie on AMS and regular paging. So what is the problem that AMS is going to look at? Well, I've got 3 typical scenarios where I've found that AMS will be particularly useful. If you have any of these problems, then you should find AMS useful to you too. The first problem is, where is the spare memory in a machine? So in this little example here, perhaps you have 100 logical partitions. They're all fairly standard, and now you've been asked to run an extra logical partition. You can look at the CPU pool. You're using shared CPUs, I hope, and you can see how much spare capacity you have, and you can see that you can add an extra LPAR. But how do you find the spare memory in the machine? It's actually very difficult to determine. AIX is pretty good at using all the memory it gives you, but it may be sitting on memory pages that it hasn't used for quite a long time, maybe hours, maybe days, maybe weeks. It's actually used the memory page to try and avoid I/O, but it doesn't really need it, and we could use that memory for this new logical partition. This is a place where AMS can help out. It can track down the memory that was least recently used and allocate that into your new logic. Problem number 2 is, if you're a solution designer, for each of your logical partitions on a large machine, you have to decide how much memory to use. You may think that 10 gigabytes sounds about right. You may have a standard policy that every application server gets a certain size of memory. Maybe you've asked the application vendor what they recommend. Maybe you're adding a bit for safety just to make sure that it's going to work nicely. But we have to admit that it is a bit of an estimate, a bit of a guess, and we're just trying our best to find a good solution. Then we add it all up, and let's say we get to 280 gigabytes. We think, oh dear, that means we need to use the very biggest memory DIMMs. That has 2 implications. One is that the cost goes up. They cost more than double the next size down, and it means we'll have a reduced number of them, which means a slightly reduced performance. If only we could squeeze the memory down a bit and we could get below 256 gigabytes, then we could use the smaller DIMMs. The costs go down and the performance might actually go up. Well, again, this is a place where AMS can help out. It can automatically balance the memory across our logical partitions based on real use rather than our guesstimates. Problem number 3 is that we may size our logical partitions, but they don't stay static in time. For example, if we got a round the world type system where different logical partitions are used at different parts of the day because their users are in different parts of the world, or we have daytime and nighttime, maybe online during the day to the users and batch at night, or we have infrequently used. A lot of people have test and dev and training and all sorts of different databases and systems, and a lot of them aren't used at the same time. We just want to push the memory into the one that's actually in use at the moment. And we also have a case where we have a failover logical partition. It doesn't actually need much memory while it's just sitting there, but it's when we have a failover we want to rapidly grow up the amount of memory and take it from other logical partitions on demand. Again, this is a place where AMS can really help by paging memory from one logical partition into the next. Now we're very quickly going to go through setup. There is another movie that goes through the details. We're just going to go through this very simply as a sort of black box exercise. If we're using AMS, first note that you can still have dedicated memory logical partitions. At least one of them has to be dedicated. For example, the virtual I/O server needs some real memory. Then we set up the shared memory pool. It's a similar concept to the shared CPU pool. We can give it a particular size, and we can set the maximum size. That's used as a sanity check because we can dynamically change the size of the memory pool. Then we're going to allocate the VIO server that's actually going to do the paging in and out of the pool, and it will need a set of devices, one for every logical partition that's using the memory pool. These devices can be a logical volume on a VIO server disk, it can be a whole disk, a H disk, SCSI, SAN or whatever, and we can also use a LUN on a fiber channel disk subsystem. Then we can create more logical partitions, allocate them shared memory rather than dedicated memory, and they take that memory out of the memory pool. Now I want to work through a small worked example to see how we can actually create our logical partitions and use the memory between them. In this example then, we're going to have a 32 gigabyte machine. The hypervisor is going to use some memory. We're going to have some dedicated logical partitions. They'll have some memory. The VIO server will take a little bit, and the rest of it we're going to put in the pool. So we're going to end up with 24 gigabytes of memory in the pool. We're going to create more logical partitions to use that pool. So let's use 4 8 gigabyte logical partitions. Now you'll immediately see that we have 24 gigabytes of real memory, and those logical partitions have what's called logical memory now, and that's actually larger than the physical memory. So we have to be careful how we fit these logical partitions into the available memory. Now there's a couple of situations that we'll look through. Now if we only start 3 of the logical partitions, then everything fits. So that's going to work fine. We won't actually have to do much with AMS. If we start up all 4 and the residence size, the residence set, is roughly 24 gigabytes, the size of the memory pool, then this will work fine. Everything will actually fit in the memory pool and work. If we go slightly over the size, the residence set is slightly larger than the physical memory, then we're going to have to do some paging. We know with the 5 golden rules how to actually make the paging work well. If we, however, go well over the size of the memory pool, then we are going to get into serious paging difficulties, and we'll look at various things we can do to help out and solve that problem. Now let's look at those 4 situations in more detail and what AMS is going to do in each of those situations. Well, the first one is where everything fits into the pool, so we don't have to do anything. The AIX may do some paging to their local paging spaces, not an issue. AMS is really relaxed and everything's really cool. If things nearly fit, then the hypervisor will ask the operating systems for a bit of assistance, and once a second the AIX will check to see if the hypervisor needs some help, and if necessary it will do some paging out of its pages and loan memory pages to the hypervisor. The hypervisor then can give those pages to a logical partition in higher demand for memory. So here AIX is helping out the hypervisor, and it's cooperating amongst its peer logical partitions. There are some tuning options in here on how aggressively AIX will actually try to free up memory for its friends. So if we start off here that everything fits well and we're just running, this will all fit in here, some free memory inside each of the AIX operating systems. Then perhaps this one goes busy. Perhaps we start a job or another 1,000 users arrive and we need more memory and we run out of memory, so we're starting to page heavily in this logical partition. Well, we can change the logical memory of a logical partition on the fly, so perhaps we add 2 more gigabytes of logical memory. But now note we're using 26 gigabytes of logical memory, but we've only actually got 24 gigabytes in the pool. So how do we actually do that? Well, this is where the hypervisor asks the other copies of AIX to help out, and they agree to free up the memory and loan it to the hypervisor, and the hypervisor can use those memory pages to give the logical partition that's struggling extra memory pages. Perhaps then we start another logical partition, and we're definitely overcommitted now in our memory pool, and again the hypervisor can ask the running logical partitions, can you loan some more? So perhaps they can free up some more space, loan extra memory to it, and we can start up this 4th logical partition. When loans are not enough. Now we've got a problem here. We've tried to cooperate and it doesn't work, so the hypervisor gets more aggressive. What it will do is it will steal pages from the operating systems, it can see the page table because it owns the page tables in the machine. It will avoid critical memory pages that actually have to be there because they're highlighted in the page tables. It will be using the least recently used algorithm to find out the memory pages that are oldest in the machine, and it will use the VIO server to page out the memory from the logical partition. Once that has happened, the page is actually free, and it will give that page to the logical partition that actually has high demand for memory. The logical partitions are not aware of this happening. This is what we call a more aggressive mode. Now, what happens when a logical partition accesses a memory page that's not present because it's been stolen by AMS and put on the VIO server paging spaces? Well, normally the hypervisor handles the interrupts for page faults, and then it hands those to the logical partition involved. So before handing them on, it checks, is this a page that the hypervisor itself has paged out? If the answer is yes, then it asks the VIO server to recover the page and put it back into memory, and then it restarts the instruction that caused the page fault, and off it goes. If it isn't a page that the hypervisor stole, then it's something to do with the page fault in the actual copy of AIX running, and so it passes the page fault onto the copy of AIX, and it handles the paging algorithm as normal. So in this example here, we started up a new logical partition. It needs some memory. Loaning wasn't enough to satisfy that memory requirement, so the hypervisor has gone more aggressive. It's paged out these little holes we can see in the operating systems, in the logical partitions, pushed those pages out onto the VIO server, and then it can hand the now free memory pages to this new logical partition. Eventually we get into a sort of steady state where the hypervisor will be stealing some pages regularly from an operating system, and the operating system will be demand paging those back in because it's touched those pages. And over time, memory pages will flow from one logical partition that hasn't got high demand for memory to the logical partition that has high demand for memory. It will be paging these in and out via the VIO server. Now, if things get really bad, we've seriously overcommitted our memory, or the residence sets have got far too large for the amount of physical memory we have, what can we actually do about that? Well, we can try and live with it, and we can spread our paging spaces in our VIO server across as many disks as possible. Maybe on the disk subsystems we try and spread the data out further as well, just to increase the rate at which we can do paging. We could add memory to the shared memory pool. If necessary, perhaps we have to remove it from the dedicated memory logical partitions to boost the size of the shared pool. We could reduce the memory requirements. Perhaps some of the applications can be tuned down to use less memory, so there's less pressure on memory. We could actually stop a logical partition. That would free up all the memory in that logical partition. We could use partition mobility, jump one of our logical partitions using the shared memory to a different machine, which hopefully has more memory available. Or we could buy more memory, do a capacity upgrade on demand on the larger machines. There are some places where AMS would not make sense. Anything that has very high sustained memory resident requirement. For example, high performance computing quite often is very memory intensive, and they won't be using AMS. Also, large databases can have a large cache full of the disk blocks. They don't like these being paged out at all, particularly if they're using all of the memory inside that cache very frequently. There are also some workloads that paging is just really not an option anyway. There's real-time applications or response time sensitive applications, and some applications that they don't mind what the response time is, but they need it to be very predictable. And it usually can't tolerate the fact that AMS has paged things out behind the covers and it wouldn't know about it. Now here's the example we used in a previous movie of the virtual memory of a logical partition. Some of it will be in physical memory and some will be on the disk. And this picture at the logical partition level now changes a little bit more complicated. So here, instead of the physical memory of a logical partition, we now have what's called logical memory. The white square in the blue there is the memory that it's agreed to loan to the hypervisor, and so that is missing out of our logical memory at the moment. We could demand that back if we needed to. We also have little pages removed by the hypervisor and sent to the disks on the VIO server, so we have little holes inside our logical memory that we're not really aware of. We've also noted here the commands we can use to actually find out the sizes of these things. We'll look at that more in a monitoring and performance tuning movie for AMS. Well, I hope that's got some of the concepts ready for when you try active memory sharing, and with that foundation we should be able to understand what's going on when we actually look at AMS while it's running.